last time we finished the 4 integrals that we used to split this big integral right here. And we used different methods of integration. We split it into 4 smaller problems. We did the 4 problems separately. And well, now that we have everything pretty much, let's put it back into where it corresponds. So for the first integral we did a u substitution. So that's going to be, well, I'm going to use the lower side here. So what was that? It's 1/2 ln of, well, in this case again we don't need absolute value bars, x squared plus 4 plus 1/2 arctan of x over 2. Now for the remaining 2 integrals, recall that we skipped a couple of factors of -4 and +4, I think. They were -4. So that was -4 times, okay, what was the result for the third integral? The result for the third integral, which was this, so that becomes minus, what was that? It was 1/2. Okay, let me check it again. 1/2 x squared plus 4 plus the result of the last integral, which in this case is okay, let me make this smaller, closer, and whoops, plus, or actually -4 times 1/16, which is this result we got last time. Arctan x over 2 plus x over 8 x squared plus 4. So all we need, in this case plus c, because that's finally the last result here. So all we need is to simplify this. Actually we have a couple of like terms and some simplification. So in this case we can divide out 4/2, that's 2/1. We can divide 16 and 4, that's 1 and 4. And 4 and 8, that's also 1 and 2. So let's just copy whatever we were left with rather. And that's actually minus 1/x squared, or rather 2 x squared plus 4, and minus 1/4 arctan x over 2, and minus 4x over 2, which is rather minus x over 2 x squared plus 4 plus c. And we're almost done, we're almost there, except that we can combine a couple of like terms, actually these two. So we're going to have a 1/2 minus 1/4. Doesn't that reduce to 1/4? So 1/2 ln x squared plus 4 and plus 1/4 arctan x over 2 minus 2 over x squared plus 4 minus x over 2 x squared plus 4 plus c. And that's final answer for this last problem. And well, if you might wonder yourself if you're ever gonna get anything like this on an exam, on a quiz. Well, the answer is no. So you think about it, it actually took us a span of 2 lectures to go through this. But the reason why I chose this exercise to do it in class, it's because notice how we use many different methods of integration that help us review pretty much everything to keep it fresh. So when the next exam comes, it's still resonating all the time, all right? In the meantime, let's move on to a new section. That section is 7.8, improper integrals. So notice how we go from what is that, section 7.4, I believe it is, to 7.8. That's because the sections in between are sections in which we use formulas to integrate, to evaluate integrals, and numerical methods to evaluate those integrals which are not part of what we do in this class. All right. So what about improper integrals? So there's two types of improper integrals. Number one, type 1 is when we have limits of integration that are infinite, and type 2 in which there is a discontinuity, like in the form of an asymptote, somewhere in between the interval of integration. Now, the rules that we're going to use are going to be the same. There's really no new rules of integration. It's more about the notation. For example, back to the integrals that we have done before, we have f of x, and this is from a to b. So the integral from f of x with respect x from a to b, which gave us the area under the curve, that's going to give us big F of x evaluated from a to b. That means big F of b minus big F of a. So that's fundamental theorem of calculus. That's what we have done for a while. We have used this theorem, or this definition, to compute some of the integrals related to areas between curves, under the curves, volumes of solids of revolution, same idea. However, the issue is if one of the limits of integration is infinity. So, for example, what if we have the integral from 0 to infinity, big F of, little f of x dx? Well, technically we should get an antiderivative, which is denoted big F, and we evaluate it from 0 to infinity. There's something wrong over here. Even though that's technically the fundamental theorem of calculus, the issue with this is that we cannot do operations with infinity. We cannot treat the infinity symbol as a number, because the infinity symbol, or infinite, it's really not a number. It's just a symbol to give us an idea of something that never ends, and therefore, well, since we don't know its value, we don't know how big it is, we cannot treat it like an actual number, like 5, 17, 59 million, we cannot treat it like this. It's just an infinity. Instead, well, so in order to connect this idea of something that never ends, what we do instead is treat the problem like a limit problem. So that's why we have this limit notation. And yes, in the end, we're going to plug it in, f of b minus f of a in a way. But again, there's a big difference between evaluating a function and evaluating a limit. Evaluating a function is whether the point is defined, or whether we can stand at a given point. However, a limit is computed just so we can get an idea of where are we approaching, where are we getting to as we approach a certain value. It's, even though the mechanics, the algebraic manipulations are very similar to plugging in the value, but conceptual wise, these are two different things. And in this case, for improper integrals, we need to treat this in a different notation. All right, so we're going to compute a couple of improper integrals, and well, yes, we're going to find the area under the curve from some value to infinity, and in this case, well, depending on the result, so we're going to compute a limit, and depending on the result, if the limit it's a natural number, like 0, 5, 7, whatever that value is, well, we say that since the limit exists, the integral converges. But otherwise, if the integral leads to a limit that goes to infinity, or d and e, well, then we say that the improper integral is divergent. All right, so let's have a look at some examples, and we're going to do the first case of type 1 in which the upper limit is the infinite symbol. Then we're going to do the second case in which the lower limit is infinity, and then the third case in which both limits of integration are actually infinity. In other words, we're integrating over the whole real number line. So yes, these integrals look like really innocent. It's just the notation that we're going to care about. So for example, by the way, never mind. Okay, so we're going to replace this infinity in the upper limit, because again, we cannot treat that infinity as an actual number. It's just an idea of something that never ends. And the best way to deal with it is by means of a limit. So, limit of the integral between 1 and b as b approaches infinity. And at the same time, I'm going to move this x to the x squared in the denominator rather, to the numerator with negative exponent, so we can integrate this one. All right. So using the general power rule, well, the integral of x to the negative 2, that's limit b approaching infinity of x to the negative 1 over negative 1. This evaluated from 1 to b. Okay? Well, let's clean up these negatives and all that so it's easier for us to work it with. Now, this negative 1, just so we don't get any trouble or any issues with the negative signs, I'm gonna write it in front of the limit expression. In fact, it's a multiple constant, negative 1. Negative limit b approaches infinity. That's 1 over x from 1 to b. So we're going to use the fundamental theorem of calculus again. F of b minus f of a. That's a negative limit b approaches infinity. 1 over b minus 1 over 1. Well, in this case, we are not evaluating a function. Notice, we are computing a limit. And well, so where is this term going to go to when b equals to 0? It's going to go to 0, isn't it? Yeah. So that's going to leave us with negative 0 minus 1, which results into 1. Alright, so this is the area under that curve, and in this case, because we got a finite number, we say that the integral converges. Alright, so the integral converges in this case. Let's have a look at the next example and see what's going to happen this time. So again, we have the integral between 1 and infinity of 1 over the square root of x. So the number one thing what we want to do is write this as a limit problem. So that's the limit b approaches infinity, and replace the limit the upper limit with the b. And at the same time, I'm going to write this root of x that it's in the denominator as a rational exponent. That's the same as saying x to the 1/2. And then I'm going to move this to the numerator with negative exponent. This way we can integrate this, all right? Because we cannot integrate while the variable is in the denominator, unless we have a great setting in which a u du works nicely. But it's not the case in this one. So let's compute the limit. So that's the limit. We keep writing the limit notation until we compute it in the end. So that's x to the, negative 1/2. We need to add 1 to the exponent. So that's going to give us 1/2 over 1/2 from 1 to b. Okay. Number 1. Dividing by 1/2. It's the same as multiplying by the reciprocal. In that That's true for any division by any fraction. Dividing by a fraction is the same as multiplying by the reciprocal of that rational number. In this case, the reciprocal of 1/2 is the number 2, but because it's a multiple constant, I'm just going to write it in front of the limit expression. And also, I'm going to go back to radical notation. So let's see over here. So upper limit minus lower limit, the usual, the same. And that's the square root of b minus the square root of 1. But this time, where is this limit going to? Is this limit going to 0 just like the previous one? Where is it going to? Infinity, right? Well, infinity minus the square root of 1, well, subtracting 1, it's not going to do any harm. And on top of that, multiplied by 2, well, it's going to get a bigger infinity, all right? So just call it infinity. And in this case, well, we're not getting a finite number as a final result. Therefore, we say that the integral diverges. All right? The integral diverges in this case. So, as we can tell, I mean, we're using the same integration techniques, no new formulas. It's just the way we treat the problem that involves an infinity. Instead, we're treating it like a limit problem. Yes, we still do this fundamental theorem of calculus, but instead of plugging in a value, that limit notation actually is here to save the day. All right? Okay. What if this time we integrate from negative infinity to a given value? So in this case, well, we're integrating to infinity to the left. We're getting this infinite area. So here's the picture, all this infinite area. And in some cases, again, depending on the value of the limit that we obtain, the integral again converges if the limit exists, if we get a finite value, but otherwise the improper integral diverges if the limit does not exist or if we don't get a finite value. So let's go ahead and look at some examples. And the notation this time is going to change. Notice for the first case, the upper limit was positive infinity. And that corresponded to b going to infinity. In this case, it is the lower limit, which is negative infinity. And because usually the lower limit is related to the a value, because we integrate from a to b, so that's the lower limit. So this time, our limit is going to be from a, as a is approaching negative infinity. Everything else is going to be just about the same. So let's do an example. Let's see how we set it up. So we have the integral from negative infinity to 3. All right. So let's see the integral from negative infinity to 3. And, well, yeah, that's fine. So that's limit as a approaches negative infinity of the integral from a, because we're replacing that negative infinity, which is the lower limit, with an a, which will represent that value, to 3. And at the same time, I'm going to have this x to the 4th. I write it in the numerator with negative exponent. Only then we will be able to integrate this, right? And integrating this, that's the limit as a approaches negative infinity, and adding 1 to the exponent, that should be x to the negative 3 over negative 3 evaluated from a to 3. Well, I'm going to take this constant multiple outside of the integral, and that's negative 1/3 limit 1 over x cubed from a to 3 as a approaches negative infinity. The rest is exactly the same. It's pretty much the same. Upper limit minus lower limit. That is negative 1/3 limit a approaches negative infinity. So that's going to be 1/3 cubed minus 1/a cubed. And well, 1/3 cubed, that should give us 27. However, what is this again going to go? 0, which is great, all right? So that means the integral will converge. So we're going to have negative 1/3 of 1/27, and that's negative 1/81. And because we got a finite value, we say that the integral converges. Otherwise, well, if we get a DNE or an infinity value, well, integral blows up to infinity and diverges. Okay. All right, anyway. Okay, does anyone remember this formula, or can recall the form that we have for this integral? Can we use substitution here? No use substitution here, right? We would be missing a factor of x here, so we have the u du setup. So, any other alternatives that you can think of? Which one?
Isn't it an identity?
Not exactly an identity. That's if we had trigonometric functions, right? Which one?
The natural log.
Not the natural log, because we would need an x here, so we can use, if we said u equals 1 plus x squared, du would be 2x, and then we would have the setup, but in this case we don't have the x right here.
And you do 1/u squared plus a squared?
1/u squared plus a squared, that looks interesting, alright? So that's quantity squared plus another quantity squared. Alright, so what quantity squared equals 1? Well, 1, and what quantity squared equals x squared? That's x. Which one? The inverse tan, right? The arctangent rule. The integral whose result is an arctangent in this case. So, but number one, we need to split this into two integrals. Number one, the integral from negative, actually we need limit notation for this. Limit a approaches negative infinity of the integral of a to, okay, we need, I'm going to do it to 0 this time. 1 plus x squared dx plus limit b approaches infinity of the integral from 0 to b of 1/1 plus x squared dx, right? So both integrals are going to give us the arctan in this case, so that's going to be number one, limit a approaches negative infinity of arctan x from a to 0 plus limit a approaches b approaches infinity arctan x evaluated from 0 to b. So let's compute these two limits. Well, actually, we don't need to do it one at a time. We can do both at the same time. Number one, so upper limit minus lower limit. So that's going to be arctan of 0 as a approaches negative infinity minus arctan of a. So that's the first limit plus the second limit, but this time b approaching positive infinity, and that's arctan of b minus arctan of 0. Alright, so I guess the easiest quantity here to compute is the arctangent of 0. In other words, what angle has a tangent equals 0? Where is that going to go to? 0. However, what is arctangent at infinity and what is arctangent at negative infinity? That'll be the question here. Any ideas of what's arctangent of infinity? Is it infinity? Would this blow up to infinity? Pi over 2? Alright. Well, where is this coming from? Number one. So it would be a good idea to recall where is this graph coming from. Well, recall that the tangent function looks like this. And we have vertical asymptotes, negative pi over 2 to pi over 2, and then 3 pi over 2, actually at odd multiples of pi over 2. Well, of course, we want this arctan function represents the inverse function of the tangent function. But in order to have an inverse function, we need to make sure that the function is one-to-one. In other words, the graph, from the graphic representation, it passes the horizontal line test. That is, the horizontal line must cross only once. So at first glance, this function fails to be one-to-one. So for this reason, we need to restrict the domain of the tangent function to only negative pi over 2 to pi over 2, and only then we will be able to define an inverse function for tangent. Now, what's the end result? So, the new arctangent function looks like this, and these two vertical asymptotes here become horizontal asymptotes at the same values, pi over 2 and negative pi over 2, above and below. Well, this means that when we evaluate these limits at infinity, well, if we approach infinity, this will get asymptotically close to an upper bound named pi over 2. And if we go for the limit towards negative infinity, it's going to be the same, but in this case, negative pi over 2. So coming back to computing the limit, we will obtain then, this one is going to go to negative pi over 2. This one is going to go to pi over 2. Now be careful, negative times a negative, it's going to be positive pi over 2 plus pi over 2, and this is going to be pi. Therefore, our integral converges and converges to pi. Alright, so next time I'm going to go over a different example in which, or I'm just going to set up, not going to go over the whole problem, in which we will need to change this 0 into a different value. So depending on the need, we may need to change it, but for simplicity we use 0.